continues on TCP today.
Professor,
Yeah.
so if you're covering TCP, there's one more lecture between midterm, right? That you're gonna cover.
Yeah. So I'm going to cover that too.
Okay, all right.
So today we're going to talk about the TCP congestion control. So we understand what is a flow control and congestion control. Flow control is end-to-end, meaning sender to receiver. Congestion control is sender, then network, then to the receiver. What's the difference? I have the exact destination, then I want to control, I want to maximize, I want to optimize between me and the receiver. But congestion control is more complex because I don't know what's going to happen in the network. Then I want to make my network status the best as possible for the general good. General good meaning I want to be good. At the same time, I don't want to hinder the others too. I don't want to be greedy, but I want a member of the network. Then I do what I can do. I want to be served the best, and also the others want to be good enough. We call the fairness. Okay, then we're gonna talk about that today. So before we go to the deeper, so from here, so we talked about the, we learned about what is the layering, why we're doing layering. Okay, and from that concept, we learn about the lower layer to the upper layer. The lower layer, we talked about how we measure the bit level performance, how we send the bits, just rather than just sending a 0 and 1, 0, 1, 0, 1. That is inefficient. We know why, because it is so prone to be error. So how are you going to encode messages? That's what we learned in the error encoding framing. And what's going to happen if the sum of the bits are contaminated? Do we have any mechanism to overcome? That is error correction. And if it needs the retransmission, when is right time to do it? Then we talked about retransmission. What if you are sharing the medium? Medium meaning you are sharing the Ethernet, you are sharing the Wi-Fi, you are sharing the backbone. Meaning, what's the best way to do sharing? Then it is multiple access. And we talked about the wireless multiple access when it goes to the Wi-Fi. And we talked about the Wi-Fi specifically, and we talked about one more upper layer, internet networking, how they connected, how the routers are connected, then how the packets are traveled in the routing. So from me to in some packets is Stony Brook. Okay, then we learned that okay, that mechanism is adaptive. Okay, it looks good, but how's it gonna work in reality? In reality, it is written rule by the administrator. Then what they count. Okay, then we talked about one more layer up, transport layer. The routing is in the layer 3. Okay, so the devices to devices. And in the transport layer, it is now I care about the me to actual destination from YouTube streaming to my computer. Okay, then we talked about the UDP and the TCP. And theoretically, UDP is a better, but UDP doesn't count the environment. So the TCP won, but these days, UDP are keep expanding its market share. But TCP was king for 15 years. Okay, then we talked about how the TCP working. Then in the TCP is more complex. Can I send it? Okay, you can. How about this? How about this? Keep collecting feedback and want to maximize, optimize the environment. Okay. Then today we're going to talk about TCP window size, TCP congestion control. It means TCP congestion control. By the name of the congestion control, we understand this is the networks in the cloud, me to destination, source to target. Okay, can I send it this big one? Meaning, can I send it multiple packets at one time? Then there is a multiple entities who take care, and the receiver keep digesting, keep digesting. What if I'm so greedy? I can send a big one. I don't care about the others. Then the receiver may receive it, but it starves. meaning it experienced the poor experience. Why? Because the senders sending more packets, bigger packets than the receiver can digest. Okay, then what's how the TCP working? Oh, how about this size and collect the feedback? How about this size, collect the feedback? Oh, now you can digest this much. How about this one? Keep communicating. Then we call this size as congestion window size, CWND. Okay, we're going to talk about this today. So TCP congestion control. TCP CC is the essential strategy of the CC is the TCP hosts the sender packet into the network. Oh, now we talked about into the network. Previously, we talked about sender to receiver. Now we are living in a little more complex. Then we talked about into the network. Without a reservation, then the host reacts to observable event. Why is the reservation is a so let's talk about reservation on network. Is it good? Is it bad? What's the concept of reservation on the network? Meaning, I'm gonna send this packet. I'm gonna initiate this packet, which means anyone else, please notice, I'm gonna send a big one. So you have to be shrink your packet or keep quiet. Okay, that is a reservation concept. Is it good or is it bad? Is it even possible? Let's talk about this. Just warm up our brain. What do you think? You understand the concept, right? So the concept is, so what do you mean reservation? What do you mean without reservation? What do you mean network reservation? Network reservation meaning, hey, I'm gonna send this packet at this time, so everyone else should be quiet. Or should be shrink your packet size. Okay. Is it good for network? Or is it bad for network? Is it even possible? Okay, let's think about this. Okay, I'm gonna pick the student. Who was quiet so far. Okay, Chungmin and Jaewon and Ulbeck. Any thought?
Can I go, Professor?
Yeah, sure.
I think it's good,
Good.
because we are establishing time, and other say we know that server sending package. So let's say others will not like expect package that time. So it's kind of good.
Common network or LP. So I'm gonna explain it in two different ways. Is it good? Is it bad? Is it possible? Is it good? Bad? Or possible? So the antonym for network reservation is best effort. Okay, anyone else? Thank you, Ulbeck. Ulbeck said it is good. And Chungmin? Lee Jae-won?
For me, I think instead of just reserving the time for like one client, I think it's much better to like have a sliding window so that we can handle multiple clients, because like the server can like handle like multiple clients at the same time, right? Like even though the even though it cannot handle thousands of requests, it can probably handle like 100, right?
Mm.
So something like that,
So
maybe.
you prefer to do the competition?
Kind of like a small sliding windows of manageable size.
So our team is also wrote something, I think a bit bad, because it may create a network traffic causing problem when there are many users are using it. Okay, Kim is said it's bad. Team. What do you think? So anyone else?
Professor, this is
Yeah.
me.
Okay.
And also, I think common network is not good because
Not good.
Yeah.
Why?
because many user can like use it at the same time and then it can be like traffic free.
Okay, I'm sorry. It's hard to understand the some lousy environment. Sorry, I don't get the point. But what you are saying is, can you say that again, please?
I think it's like almost similar to previous like opinions.
So you mean that you are saying to the teams?
Yes.
Okay. All right, sir. Okay. Thank you. Thank you all. So let's think about it this way. So network reservation and best effort. So we can assume our backbone is wide enough. Is usually 10G or 20G. Okay. That is, let's say one user may use 1G or less at best. And we are assuming this environment. Okay. In reality, it may differ. But assume this. What's the bad side of network reservation? There is a greedy guy who keep reserving, who keep trying to reserve it. And they want to allocate, let's say 50% of them for their purpose. Then what happened to the others? The others has to compete on the rest of 50. Then we call this fairness issue. Fairness. Fairness meaning network should provide good enough resources to the members. At the same time, it should provide the fair opportunity for everybody. Okay, so let's talk about common network. Common network meaning while there is some reservation I cannot access, and there is a delay gap. So reserve it and use it, reserve it and use it. And I need to have one controller, right? Someone who make a reservation in the end. But how's the network look like? Network is not controlled by the one guy. Network is controlled by multiple guys. It is connected by the multiple entities. Think about my packets from me to the Stony Brook, from SUNY Crest to the Stony Brook. It is impossible to have the one controller who assigned everything in the middle. So it's very hard to reserve it. Also, it is if there is some greedy users, it is very hard to prevent them. Okay. How about LTE? LTE called 4G or 5G. What's the difference between common network and 4G and 5G? We are paying. Meaning, so I am mobile user. So networks, so common network is in the cloud. I'm connected. Okay, I'm connected. So how about LTE look like? LTE is a set of base station. Set of base station. So SKT, 송도 1, SKT, 송도 2, SKT, 송도 3. Okay, so whenever we are depleting the LTE or cellular network, we are using the honeycomb. That is how we use it. Oh. So this is how it's designed. Why? They are, so let's say this is Korea, South Korea. In Seoul, there are many users. What do I have to do? I need to make my honeycomb smaller, because in a given environment, there are multiple users. What about in the middle of this, somewhere like this? I can make my grid, my honeycomb bigger, because there's less people using it. Okay, this is not exactly related to the subject, but what I want to say is LTE and mobile thing is different because I need to provide the phone call. Phone call meaning if the phone call is the congestion based, then I may connect it or not connected, connected or not connected. Okay, so I need to provide consistent. Okay, as long as that also your SKT has a control, the main controller. Okay, so from you or phone to base station, and base station is controlled by SKT center control, and they connect it to the others. So it is network, common network, but until this point, it is 4G network. Okay, so I need to have consistent quality, right? So I need to have the good enough quality that I can talk to someone. Let's say I want to talk to the KT. So they are connected because they only have 3 of them, LGT. They are connected, then they go to their honeycomb and they are connected. So from here to here is guarantee based. Here to here is a guarantee based. Then it is its architecture is able to provide the central controller, only 2 of them. What if I'm talk to from SKT to Verizon in US? Verizon has their honeycomb and base station. And SKT to the Verizon is a wide backbone. Okay, they don't use a common, but they have a wide backbone. And from here to here, here to here, they can control. And with only 2 entities, we can control. But in a common network, that is not able to control. Okay, so if I'm saying, okay, in a common network reservation not even possible. In the LTE or 4G network, it is reservation must be considered, and it is possible, and it is good. All right, go to the point. So congestion control originally assumes first in, first out, and basic idea of it, and source determines how much capacity is available in a given floor in the networks. X, your feedbacks are used to pace the transmission of packets such that TCP is self-clocking, meaning, can I send this much? If I'm collected X in a given time, oh, he is fine, then maybe I can increase, or if it is something bad, I have to shrink it, okay? So we called AIMD. AIMD is nothing different, but additive increase, multiplicative decrease, meaning if I'm sending from source to destination, keep sending it. If the receiver keeps sending me an ACK, meaning, oh, you are fine. You are satisfied. You can you can control, and you can digest my sent packet properly. Okay, thank you. Can I send it? Okay, thank you, and well received, well received. Then what can I do? I can increase more. I can at this time I try this, a little bigger one. Okay, he's still digesting. Oh, try this, a little bigger one. Oh, still digesting. Oh, I sent a big one. Then he's not able to digesting. Then what do I face? Maybe I'm facing a timeout. Timeout meaning I was waiting for the egg in a given time, but he is too busy to digest it or something bad happened. Then I have to decrease it. Then how can I decrease it? When I'm adding it, I'm adding a little bit, a little bit, a little bit, a little bit. then we call additive increase. If there's something bad, by decreasing a little bit, then it's not helping because he's already clocked, right? Then therefore I have to halving it, or I have to make it very small as possible. Okay, I'm sorry, I sent it too big last time. How about this one? Okay, or it could happen by the timeout or the duplicate ACK. When does duplicate ACK happen? Duplicate ACK meaning, okay, packet 1, 2, 3 is happen. Okay, send packet ACK 1. Then I can send the, let's say, size of window size of 3. Then I'm sending 4, right? If I'm receiving 1 egg again and 1 egg again, which means my packet 2 is missing. Okay, something missing, which means network environment is not good. Okay, it's a implicit way to know the network state is not good. Okay, I have to send it back again from the 2. Then I can increase it or no. Okay, so timeout or duplicate egg is the feedback that I can notice that something is not good. Okay, something good is I'm collecting egg periodically in the given environment. Okay, then I can increase some of these 2. If one of these 2 happen, then I have to decrease. Oh, I think I sent a too big one. Okay, so that's the concept of AIMD. So congestion window size, we call the CWND, is a variable held by TCP source for each connection. Okay, so maximum window size is a smaller one between congestion window or advertised window. Actual effective window is maximum window size subtracted by last byte sent and last byte act. Okay, we will gonna talk about this. It's a variable, how it's set. Okay, CWND is a set based on the perceived the level of congestion. The host receive implicit or explicit indication of internal congestion. Implicit is something like packet dropped, like a 3 duplicate ACK, or explicit packet mark, something like a timeout or a neck. Okay, so AI is additive increase. Additive increase is reaction to the perceived available capacity. Okay, he was fine. I can increase a little bit. He was fine. I can increase a little bit. But what's the multiplicative increase? He was fine. I'm doubling. He was fine. I'm doubling. I can increase in a fast way, but at the same time, my risk is higher. Additive increase is I can send my the speed of increasing is smaller, but I can avoid the extent, right? I can avoid the packet drop in a low probability. So linear increase is additive increase. Linear increase, the basic idea is for each CWND worth of packet sent, increases CWND by 1. So increment just 1, increment just 1. So in practice, CWND is incremented fractionally for each arriving ACK. So increment is a fraction of this CWND plus increment. So it should be a discrete value. So in practice, it's usually 1. Okay, so additive increase. Okay, source sending it. If I'm receiving the ACK, then I'm sending 2. If they're receiving 2, oh, I can send 3. Oh, all ACK, then I can send 4. All ACK, then I'm sending 5. That's additive increase. Okay. So multiplicative decrease. Okay, when I'm adding it, when I increase my packet size, I do multiplicative additive, slowly increase it. Something bad happened, I should drop it, halving it or the lowest possible. Okay, so the key assumption is that drop packets and Resultant of the timeout drop packet is 3 duplicate ACK. Resultant timeout are due to the congestion at a router or switch. Okay, so multiplicative decrease, the TCP reacts to the timeout by halving CWND. Halving means you cut the size of the packet you sent to the half. Okay, although CWND defined in a byte, the literature often discuss the congestion control in terms of packet. So it usually one packet level. So CWND is not below the size of the single packet. Okay, you cannot divide the size of the packet because 1 is the smallest unit. So then that is AIMD. It has been shown that AIMD is a necessary condition for TCP congestion control to be stable. With this AIMD, TCP and your network is stable. Okay, if the network is okay, so I'm keep increasing. If the network goes down, I'm decreasing dramatically. Then avoid more problem. Okay, because the simple CC mechanism involves the timeout that causes retransmission. And it is important that the host have an accurate timeout mechanism. Oh, so we are using timeout and packet drop. So timeout, how you design your timeout more precisely. So we need to have precise and accurate timeout. Therefore, I can make my AIMD and TCP congestion control precisely. Okay, timeout set as a function of average RTT round trip time and standard deviation of the RTT. This gives me the information of my network. If my network is good, meaning my average RTT is smaller, I can send more packet. Okay, something like this. Okay. However, TCP host only sample the round trip type once per RTT using coarse grained clock. Okay, meaning what I can collect is not the fine level. The feedback is periodically coming. Not every time I can collect. Okay. So this is the typical TCP sawtooth pattern. I'm going to show you. So I'm sending packet size 1. It was fine. Then I'm increasing to 2. It was fine. I'm keep increasing until something bad happens. Something bad could be timeout or 3 duplicate. Okay, let something bad happen. What do? I do MD. MD meaning I'm halving the size of my packet. Then,
Professor?
Yeah.
Sorry to interrupt, but
No problem.
why does the bad thing happen? Like, is it because it's congested?
Oh, okay. Why bad thing happened? So you are using the network,
Yeah.
sender and receiver, and you are not controlling network, and you don't know what's inside. What I do know is from sender to receiver, if I'm sending it, oh, can I collect an ACK properly? That's what I know. Okay, so when I send the packet, they are replying. Okay, oh, here's receipt. Where receipt? Okay, oh, you look like you can digest more. So this network digests more, meaning at the first time I'm sending 1, then I can send 2 at the time. By sending 2, your network efficiency doubles. Previously, I only sent 1 packet, but now it is 2 packets. So I'm
by 2.
Yeah.
I'm sorry. By 2, do you mean increasing the size of the packet by 2, or is it sending packet twice?
So unit is a packet. So you have information from 1 to 10. Let's say this is your YouTube BTS music video. Music video 1 section to the 10 section, meaning from 1 second to 10 second, 11 second to 20 second, and let's say it is 90 second to 100 second. Okay, so you send this one first. By sending 1 packet, it takes too long. But what if I'm sending size of 2? Then it's more efficient. You can deliver 2 times faster. Oh, how about 4 times? You can deliver much faster, right? But
your unit of
size. Yeah. So you send the 2 big one. Let's say you send the 8 of them. Your network cannot handle properly. So something bad happened. It is not collecting the ACK in a given time, or you are receiving duplicate ACK. Okay, so you should know the receiver's environment, but it is not possible to know the whole path. So you are guessing it by feedback. Feedback is an ACK. If there's something good happen, oh, I'm keep increasing, because you can digest it. So increase, let's say this is capacity is a cap. So this is your network environment, and this is time. And the best way to do is utilize your network best. So if I know all the variable in the network, so I'm just sending the biggest possible, then keep consistently using it. But in reality, it is not possible to know every environment. So I'm sending this size. Oh, it was fine. Sending this side, it was fine. I'm keep increasing. Then after this, your network cannot handle. So you go to down and go to up and down, up and down. So in the long view, by doing this, you can fully utilize your network.
What determines the capacity? Is it the router's capacity, buffer size?
Let me use the capacity. What's the network capacity? Network capacity is one of the most important thing of network capacity is time variant. Time variant meaning, so I have a one router. So from Google CDN, Contents Divided Network, to my notebook. Let's say I'm watching BTS music video. I'm fetching the contents to my network. Okay, so in the network handles so many things. They are existing not because of me, but because of the general good. So sometimes there is multiple users are connected. They are keep receiving big file, but sometimes they don't. Sometimes big file and sometimes they don't. Therefore, it's time variant. There's no guarantee. So capacity I can use is also changing because it's organic, is keep moving. Okay, keep changing it. Therefore, theoretical capacity is between all the routers, me to your CDN. But theoretical upper bound will never be reached because you are not the only one who's using this.
I see. So capacity is dynamically changing all the time.
Yeah. So your goal is, let's assume your capacity is here in a given short time. So let's say this packet size. What's the goal? What's the best way to do? If I know everything, oh, I can send this much at one time, then keep maintain this side. Then your utility is 100%. Okay, that's the best way. But it is not possible to do that because I don't know everything. So I know only fraction of it. Then what do I do? So from here, I'm sending in. Oh, if it was fine, okay, I do increase. Oh, you're still doing this until you cross it. Okay, you sent the bigger one, then your network cannot digest properly. Then what do I do? Oh, a little decrease. It's still not working. A little decrease, still not working, right? Keep decreasing. Oh, it starts to working. Rather than doing this, okay, keep increase. Something bad happened, then you are dropping it. Then from here, you keep increasing. You're dropping it. In doing this, by doing this, you are reaching this point. Then your utility function is about 80%, something like this. Okay, so how do you decide this curve? This path is linear increase, then we call additive increase. This path is multiplicative decrease. You are halving it. Okay, so there is many TCP. Okay, if we found today the good TCP congestion window control, then we can call TCP SK, Sydney, Korea. And there is original TCP, and we are using TCP Reno and TCP Tahoe. You can name the TCP. Okay. So how do you design? What's the algorithm for this curve? Okay. All right. Go to the point. So now we understand better these pictures. Thank you, David, for the question. I think it helps the others too.
I have one more question.
Sure.
I'm sorry, but
Sure.
there's like, does this testing, like, should I call it testing, occur during handshake, like handshake,
Mhm.
or is
Does
it
it the
does it
testing
occur?
occur handshake? Oh,
Yeah,
no.
yeah.
It's actual. Okay, let's go back to the point. So TCP does handshake. 3 times of handshake. Can I send it? Yes, you can. Okay, I'm gonna send it. Thank you. Then I'm sending it. Right? So this process. After
Okay.
handshake. In the handshake,
So it.
I'm gonna send it just to let the receiver knows I'm gonna send it. So actual size is not able to predict it because your congestion and your network size is time variant. Even you do handshake, your network environments keep changing. It's dynamically. Okay, so
Understood.
TCP congestion control is here. Okay, all right, go back to the point. So let's try to explain this picture again. So now we understand how your network can handle. So I'm additively increase my packet size, my congestion window size. Congestion window, CWND, is number of packet that I can send in one time. Send one time. Okay. Oh, something bad happened. Bad is timeout, or packet drop. Okay. Oh, so I'm halving it. Oh, I'm keep increasing until it is fine. If something bad happened, I'm halving it. So it's sawtooth pattern. So your network is keep playing in between. What do you see? Inefficient. Can you make this sawtooth better? So theoretically, the best sawtooth is something like this. Go up and stay there, and it's impossible to do. Then how can you make this? Maybe you rapidly increase, and if something bad happens, you're decreasing a little. Then you want to play with this, something like this. Do you understand the point? Okay, let's think about for 1 minute. What is David, TCP David look like? How about TCP team look like? TCP Chongmin look like? So what's your strategy? Let's think about this just for 1 minute. You understand the point? Okay, let's discuss about this. Yeah. Janar, good? Yeah. Any idea? Yep. Okay. Let's say TCP. Yeah. No, nobody.
May I take a guess?
Sure.
Can we determine like a threshold, minimum threshold between like by averaging out the top and the drop,
Mm.
like where the multiple decrease happen, and then when we find the average, and if it's a constant value, we set that as threshold. So for the future, when it drops, it doesn't drop up. I mean, it doesn't drop below that threshold, and then starts from the threshold, go back up, increase.
Okay, good point. Anyone else? So what TCP David look like? So whenever increase, you are just the increase AI, right? Whenever something bad happen, he set the threshold. Oh, it doesn't go to lower than this. Okay, so remember the max threshold in here and low threshold. So from here is keep increasing, not try to achieve the max and try to that. If there's something bad happen, rather than go to the last threshold, he updates threshold in here, then plays in here, then start to update something like this. Is that what you're saying?
Yeah.
Okay. Very good. This is what TCP David looked like. There was a TCP team. Let's read it. I think it's control increasing part dynamically. We can figure out the capacity at some earlier point. For instance, when the capacity reached, we can lower it down and lower the increasing amount from the last increment. Then we can drop the speed by a very small amount, maintaining top speed. All right. Thank you. It's very you are using the threshold. Thank you, Tim. Anyone else? So TCP team is similar to the TCP David. Okay. So there is a multiple engineers who try to solve this, and we called TCP tau. Okay, let's talk about TCP tau. We called TCP slow start. Why is it slow start? So linear additive increase takes too long to ramp up the new TCP congestion control in cold start. Cold start meaning from there was no experience. Cold start, you should start from this initial point, then increase. So whenever everything is reset, we call this cold start. So we call the cold start. In the technical term, in most of the technical or engineering term, we are using cold start or warm state and hot state. Cold start meaning everything is like not working for a while, so I need to reset everything. Warm start, I had some experience, I had some history. Then from the experience, I'm using from that point. Hot state is I'm keep working. That's hot state. It's general term in engineering field. Okay. So additive increase take too long, and I want to make fast. I want to make much faster than a threshold. And how can I do this? Doubling. Like we learned in the log and exponential. What the scientists do is doubling every time. Therefore, rather than linear increase, I can double it. Then I can ramp up much faster. Okay, that's the TCP tau. Then it looks much faster than a previous. Then why do you call this slow start? Okay, go back to the point. So we have TCP David and TCP Tim. When there was a TCP came out to the world, and there are so many TCP Yeun, TCP Jungmin, TCP Ulbach. There's so many TCPs. Most of those are focused on ramp up fast enough, ramp up in a fastest way. So most of them are like 10 times than previous, 20 times than previous. Then it's something bad, go to lower it. Then we called slow start because it is a slower than 10 times or 20 times because there were so many candidates. So by halving and by doubling it, then it is slower than radical approaches. Then we call the slow start. But it is actually not a slow start. It is much faster than linear increase. Okay, so the beginning of the TCP tau, TCP David wasn't adopted, but in the field, industry choose the TCP tau. So the slow start mechanism was edited to provide initial exponential increase in the size of CWND. So it's doubling every time. So slow start, every time egg arrives, CWND is incremented double time. CWND is effectively doubled per RTT epoch. Two slow start duration. Slow start duration is at the very beginning of the connection. We call it cold start. When the connection goes down, waiting for timeout to occur. Okay, so when there is a timeout, I do slow start. Whenever there is a cold start, I do a slow start. Okay, two cases. Oh, I'm sent one. Okay, egg receipt, I double it. Oh, good. Okay, receipt, I double the size. Okay, receipt, I double the size, double the size, double the size, double the packet per egg. Okay, that's the slow start. And slow start. In the second case, what's the second case? Second case, timeout. The source has more information. The current value of CW can be saved at the congestion threshold. Ah, you look like TCP David / team. Okay. Oh, it's using a threshold. Ah, this is known as a slow start threshold, SS threshold. Okay. So when there's a timeout, let's think about when the slow start happened in a very cold state, cold start or timeout. What's the difference between two? Cold start, I have no idea because I'm the initial point of it. I cannot use a history. But in a timeout, I had some history. Then I'm going to use that. Okay, then using that as threshold. So behavior of the TCP congestion. So increase, additive increase. So let's look at this point. So something bad happened. So I almost go to the cold start. From here, I do. This is timeout case. Let's call this timeout case. So I linearly increase fast enough, double the size, which is our slow start until when? The half the size of my successful last time. Half the size of the maximum size, half the last maximum success. Therefore, this value is my threshold. This is my threshold. So if I'm just increasing like rocket, my congestion window size will jump all over the place. I don't want that to happen. Okay. So timeout happened, then dropped. Then I do fast recover, which is my slow start. I'm doubling it until I reach my threshold. Threshold is half the size of my successful max size in the given time slot. Okay. From here, rather than SS, rather than doubling it, doubling is not going to work because I know that doubling is too big. Then what do? I do linearly increase until I face some issue or until I have no more things to do. So that you try to maintain those. Your last successful point, maintain those. You try to maintain those until bad thing happens. Once the bad thing happens, you drop to the initial point because it is timeout. And you do slow start to where the last point and the half the last point. From here, I do additive increase. This is called congestion avoidance. Congestion avoidance. Okay. This linear increase called congestion avoidance. Why? I have some experience. If I doubling it, I'm sure there will be congested, meaning my network will not work properly. So I'm avoiding those by small fraction increase, small fraction increase. Okay, so I know there's a still gap, then I can ramp up in a fast way. Then we call it slow start. Okay, after the threshold, I do avoidance. Then I try to reach the optimized point. Then I don't go to higher that point because I have some experience. I know what's going to happen if I just keep increasing. Okay, so this is the TCP tau look like. It adapt slow start. It adapt congestion avoidance. Okay, so fast bridge transmission. Fast bridge transmission is course timeout remain problem. Timeout. So fast bridge transmit was added with the TCP tau. Since the receiver responds every time a packet arrives, this implies the sender will see duplicate X. So basic idea is use duplicate X to signal lost. So if I'm receiving multiple X for the same packet, which means the packets are dropped. Okay, so fast transmission is fast read transmission. Fast read transmit is upon recipient of the 3 duplicate X, TCP sender retransmit the lost packet. Oh, I know what it is. Okay, so packet 1. Okay, packet 2. Let's say window size 4. 1, 2, 3, 4 was sent. So I'm collecting 1, 2, 2. Right? Meaning I receive 1 time, 2 time, 3 times. And duplicate X in the view of 3 times. So actual duplicate X is 4, but you are receiving 3 duplicate X. So once you're receiving multiple times of duplicate meanings, so after this, it is lost. Then you are sending packet 3. Okay, so you can do a NAC or duplicate NAC. NAC concept comes much after this point. So if I'm receiving multiple X, I do retransmit. So we call it fast retransmit. Let's see how it works. So you're reaching this point and something bad happened. 3 duplicate X. Okay, this is timeout case. This is duplicate. So let's say something bad happened. You drop the ones and you solve the duplicate X, then ramp up fast way, then you do congestion avoidance. Something bad happened. Duplicate X, you ramp it and you solve the issue by retransmitting that packet again, which is 1 packet. So maintain this period, you're solving problem. You solve the issue, then you ramp up by increase the packets, increase the CWND size, then you do this period is congestion avoidance. This is slow start, and you are solving the issue. Okay, so this is the how the TCP congestion control look like. So from here, initial state, cold start, starting as 1, you are doubling your window size. 1, okay, looks fine. 2, looks fine. 4, looks fine. 8, looks fine. You go to 16. After 16, you have some experience, which is your threshold. Threshold is half the size of the last successful, which was 32. Then your threshold is 16. Then from here, you do congestion avoidance. If I'm doubling at this point, you will experience the congestion, the network congestion. Therefore, you do congestion avoidance. So you are slowly increasing. Okay, at 20, the congestion happen. Then what do? You go to 1, initial state, then you are doing slow start again. And last time it was successful was 20, then you are making the halving of it. then your slow start stop, and from here you do congestion avoidance. Something bad happened, then go to the initial point, then keep increase until you successful. 16, go to 8. Okay, then from here you are doing congestion avoidance. Okay, so we are still wasting this much. So our goal is make this space as high enough. So let's say this was network capacity working this way. So I want to fill up as much as possible. What's the proper way to do this? We're still doing this, right? Okay, then we called fast recovery. Fast recovery was added from TCP Reno. We talked about TCP tau. Now we talked about TCP Reno. So when fast retransmission detects 3 duplicate X, start to recovery process from the congestion avoidance region and use X to pipe the pace to sending the packet. So fast recovery is after fast retransmit, half the CWND and commence the recovery from the point using the linear adaptive, the primed by left X. What does this mean? So rather than go to the 1, it's not necessary to go to the 1. So if something bad happened, I go to 1. Something bad happened, I go to 1. Hey, don't do that. It's not necessary to go to all the way down. Okay, that is halving it. This concept is halving it. So TCP Reno, slow start in the initial status. When you reach the last threshold, from here you do CA, congestion avoidance. Something bad happened. What did I did previously? I go to 1. Rather than go to 1, just go to the half of it, my previous. Okay, then from here I do congestion avoidance. Then this space will be more effectively used. I don't need to go to all the way down. Rather, I just go to the halving of it. Then I can avoid the slow start. Also, I can additively increase by doing a CA. Then if there's something bad happen, I go to, so your sawtooth is ramped up. Okay, so we call the fast recovery. So modify the slow start. Rather than go to the initial point, I go to half the point. Okay, so this makes the difference between TCP tau and TCP Reno. This is a TCP tau. So this black line is TCP tau. This red line is TCP Reno. What is more efficient? TCP Reno, right? So adaptive retransmission. So I have to retransmit. How? Retransmission is round trip time per between the host and on the network. So what make decision? So for this given TCP, what's the feedback? I can collect an egg at the same. So let's talk about bad thing. Bad thing is timeout or duplicate egg. If there's something bad happen, I have to do retransmission. So what determines this properly? Let's focus on timeout. Timeout, I sent waiting for this time. If it is collected in a given time, oh, that was good. If it's given after this, something bad happened. Okay, so my timeout window is critical for the performance of TCP. My timeout window determines the TCP's performance. Okay, so original algorithm for designing your timeout, waiting time design. So keep a running average of RTT and compute the timeout as a function of this RTT. So send the packet and keep time step. When the ACK arrives, oh, I can collect the RTT. Then I'm going to use that as my timeout. I sent it. Oh, I receive it. This is my sample RTT. I'm going to use this as my timeout, which is very sensitive. Sometimes it arrives later, or sometimes it arrives earlier. I should have some variance. It should be long enough, and I should be tight enough. How can I design it properly? Okay, that is a timeout concept and algorithm. So original algorithm is estimate RTT. So estimate RTT is your history, and sample RTT is your feedback, what we did in here, sample RTT. So alpha is 0.8 to 0.9, meaning your estimate long history used as 80% of it, and your right now, so your recent fresh one is 0.2% is feedback. So original, your timeout is almost double times of the RTT. So when there is receipt, so your timeout size is almost doubling. What's the bad thing if your timeout is too long? You're waiting too long. If it is too short, you're giving up. You are making a timeout event too frequently. Okay. So we need to have a proper algorithm. We need to have a smarter way to determine this. Okay. Then there is a KP, Karn-Faktisch algorithm. It is an obvious flaw in the original algorithm. Why? Whenever there is a retransmission, it is impossible to know whether to associate the ACK with the original package retransmission. Oh, what does this mean? So the sample original RTT, original timeout mechanism is based on sample RTT. This is the important part. Okay. So whenever you sample it, it is not proper to do. Why? In this case, you sent the packet. Oh, somehow there is retransmission. Oh, there is an ACK. Is it my RTT? Is it or my RTT? Huh. It's not clear to calculate it. What if you transmit it, exceeds some time, and you retransmit it? Right after you retransmit it, there was an ACK. Oh, there is sample RTT. Is it proper way to do? It's not, right? That there is two cases you have to explain, but the original algorithm had some experience of those. Therefore, sample RTT is not reliable. Okay, then there's a KP algorithm, and it do not measure the sample RTT when sending packets more than once. It only samples when you are sending it only once. Okay, therefore you can overcome these cases. For each retransmission, set timeout to double the last timeout. So whenever the retransmission, you double the timeout. So this is form of exponential backup. Exponential backup meaning something is not working, then you are doubling it. Something is not working, you are doubling it. Okay, that is exponential backup. If you're lost in the middle based on congestion, then I'm giving you a longer time. Okay, adaptively. So, and there's a JK algorithm. So we talked about KP. KP is the set timeout double the last timeout. So for each transmission. So JK algorithm. The problem with the original algorithm is that it did not take account the variance of the sample RTT. Sample RTT will be variance. Why? Because I'm sending multiple packets, I receive it. Sample RTT, multiple packets, I receive it. So you're in the middle network. It's too complex. It is not possible to give me consistent value of the RTT. So there is a huge variance. So I have to take it into account in your timeout design. So JK algorithm count differences between sample RTT and estimated RTT, your long history. And estimate RTT is updated with estimate RTT plus differences and delta of the differences. And deviation is delta is difference minus difference is subtracted deviances, where delta is fraction between 0 to 1. So from the JK algorithm, your small changes, your variance of the act is also counted. Okay, so JK algorithm is today's industry's choice. TCP computes a timeout using both mean and variance. So I'm keep collecting my ACK. Then I'm keep stamp. Then I'm keep collecting my RTT time. Okay, so long history. I have long history, meaning I have an estimated mean. At the same time, I have some variances. Okay, so I'm using my mean. At the same time, I'm using my deviation. So mean is 1, deviation is 4. So I can make this one is smart enough and adaptive enough, my timeout. So why is the timeout design is important? Because TCP determines based on duplicate ACK and the timeout. If you make your timeout too tight, you are creating too many timeout events. If it's too long, you are wasting your environment, right? So you have to keep handling rather than just waiting it. Okay. So David is asking, what determines the delta? Delta is a fraction of it in between 0 and 1, 0 and 1. So it's based on the network environment. If your network environment fluctuate is so heavy, then delta is a big enough. If your network is so stable, your delta is a very small number. Okay. So if the
Is there an algorithm that determines it, like how much the fluctuation like equals some number of delta?
Yes, so delta. So let's say so RTT time, round trip time, your sampled RTT time. What's it look like? It's sometimes meaning your mean and the variance. Okay. More than. If your RTT is like this, then this is your mean and the variance. And you have experienced that, oh, the variance is large and you have to count variance more. If your network is stable, variance is small, your network is stable, therefore I count less on the variance. That's how you determine the delta based on environment.
Thank you.
All right, any question? All right, so this is what I prepared today. If you have a question, you may visit my office hour, or you just knock the door. And I'm gonna post the homework, and the midterm is delayed to Wednesday. And I'm gonna cover one more class on next Monday. All right, thanks for coming today. Any question? No? All right.
Professor, when's homework due?
New homework?
Yes.
Okay, I'll make a decision properly. So it's about 2 weeks from the open.